Good afternoon, everybody. My name is Rudy Shankar. I'm the director of the Energy Systems Engineering program here at Lehigh University. And we are in the fourth seminar of a seminar series that lasts for till the end of the semester. And as I mentioned in previous seminars, if you attended them, the theme for this semester was energy transition and the practice of energy transition in different countries, different continents. The last seminar, 2 weeks ago, we had personnel from University of Uruguay, Republic University of Uruguay, talk about their transition plans, and we found that they made a very rapid acceptance of renewable energy, mainly because they don't have any natural resources like coal and oil and natural gas, as do many other countries. Today, we'll hear about the energy transition in India. And unlike the country we looked at, India is a vast country. It's the third biggest producer and user of electricity. And this change has been made in a remarkable 2 or 3 decades. They've also made a strong commitment towards aspiring to be a renewable grid by 2030, to have as much as 50% of the grid with renewables. And but right now they're in the process of transitioning. And as you can well imagine, as the third largest producer and user of electricity, that you're talking about a population of 200 to 300 million who are middle class and use electricity as a very important ingredient component of the energy portfolio. So they're using a lot of fossil-driven plants to be able to transition to a renewable, more renewable grid in the coming decade or so. And of course, now they'll be having to run these fossil plants in flexible mode, that may even cause more problems. But nevertheless, we're going to find out from today's talk, what is the status, what are some of the challenges and what are some of the opportunities. And as before, this talk will be for 90 minutes, nominally 60 minutes for presentation and 30 minutes for Q&A. But Dr. Abhyankar has very kindly accepted questions while he's talking. So while he's talking, if you had a question, please introduce yourself so that he knows who he's talking to. Okay, so let me introduce Dr. Abhyankar, who's a speaker today. He's a scientist in the Energy Markets and Policy Department at UC Berkeley, and at UC Berkeley, and a senior scientist at the India Energy and Climate Center. His research focuses on power, transport, and industrial sector decarbonization in the United States and key emerging economies such as India, China, Indonesia, and Vietnam. He regularly advises governments, regulators, and utilities in multiple countries on designing clean energy policies and programs. Dr. Abhyankar has published over 80 journal articles and research reports, and his research has been widely covered in the media. He has a PhD in environment and resources from Stanford University. Welcome, Nikit.
Thank you, Rudy, and thank you for the kind introduction, and thank you for having me speak at this seminar. So, as Rudy mentioned, what I would love is this seminar to be more interactive. So if you have any clarificatory questions, please feel free to stop me in between and ask those questions. If the question you think is more substantive in nature, that might warrant a longer discussion, then I would appreciate if you could just wait until the end of the seminar, and then we can have a more substantive discussion then. All right, so just let me know if you could see my slides. I'm assuming you can.
Yes, good.
Okay, excellent. So as Rudy mentioned, we're going to be talking about the energy transition in India over the next 20 to 30 years. What are the key opportunities and what are the challenges? So before we begin, some key numbers that Rudy has already kind of mentioned them. India is the third largest producer of electricity and energy in the world. India is also the fifth largest economy in the world, on track to become the third largest economy in the next 15 to 20 years. So it's only behind US, of course, which is number one, China, Germany, and Japan. And it is expected that over the next 15 years or so, it will overtake Japan as well as Germany. India is also home to one of the largest coal reserves in the world, and that also makes the energy transition a little bit tricky and also politically challenging. But what is the key difference between the US or other countries and India, especially around the coal transition? I will come to that when we talk in detail. So with this context, I'm going to tell you three more numbers. Okay, and we're going to talk a lot of numbers in this talk. We're going to do a lot of mental math. So just be prepared and get your strong cup of coffee. So three numbers: 30, 600, 900. 900 are the number of cars per 1,000 people in the US. 600 are the number of cars per 1,000 people in Japan, Germany, UK, France. Some are 500, some are 600, some are 550, but on average, approximately 600, give or take. So Japan, Germany, France, UK are also the countries with some of the most advanced public transport infrastructure. And 30 are the number of cars per 1,000 people in India. So it really doesn't matter which development pathway India chooses, whether it's public transport led like Japan and Germany, or a private car led such as US, a massive growth in the car ownership and transportation energy demand in general is about to occur in India as nearly 200 to 300 additional people, a country almost the size of the United States, is moved into middle class, from lower income to middle class over the next 20 years or so. And same analogy or same numbers can be said for other appliances and other energy uses as well. So the chart in the middle shows the room air conditioners per 100 urban households in China and India. That essentially means the penetration of room air conditioners in China and India. China already has more than 150 air conditioners per 100 urban households, which means that every house on average has 1.5 air conditioners. Some houses have one, some houses have two, and some houses may have none. India, on the other hand, the room AC penetration in urban India is like 20 to 25%, the blue line at the bottom. And just to remind you, one air conditioner consumes anywhere between 1 to 1.5 kilowatts of energy. So as India urbanizes fast, as temperatures rise, urban heat island effect also takes place, and incomes increase, India will most likely add nearly 300 to 400 million new air conditioners in the next 20 to 30 years. And that is equivalent to 300 to 400 gigawatts of peak demand onto the grid. And just to give you a scale of things, the entire US's peak electricity demand is approximately between 600 to 700 gigawatts. Okay. So this is essentially adding more than half the electricity grid that we have for the US in India just for one appliance, which is room air conditioner. And this is also something that has happened in China already. And we will come to that a bit later. The same numbers could be said for fossil-based power capacity, which is shown in the chart on the extreme right. So China currently has 1,400 gigawatts of coal and gas capacity, coal and gas power generation capacity. US has approximately 800 gigawatts, give or take, but coal capacity is obviously slated for retirement. But as of today, it is approximately 800 gigawatts, give or take some. And India currently has 250 gigawatts of fossil-based capacity. So again, a massive growth even in the electricity generation capacity is about to happen in India over the next 20 to 30 years. Now, what does this mean for energy transition? This has three important implications for energy transition. Implication number one is India lags nearly $2 trillion in energy assets compared to industrialized economies such as US or even China. What that implies is most of the energy transition discussion in the US, for example, is on how to transition the existing fossil fuel assets and make room for new clean energy assets. But that's not true in India. Nearly 80% of the energy infrastructure that will exist in India over the next 20, 30 years, say by 2040, 2050, is yet to be built. So India has this unique opportunity to leapfrog to a clean energy infrastructure without having to go through build fossil, develop the economy, and then clean up the energy. India doesn't have to take that middle step of build fossil and develop the economy. It can just build clean and still develop the economy. Now, the second important aspect for energy transition in India is that India is also one of the largest net energy exporters, net energy importers, in the world. In fact, not one of the largest, it is the largest net energy importer in the world. What does that mean? Is nearly 90% of India's oil is imported. India doesn't have any of its crude oil that it consumes. And that is only going to increase over the next 20, 30 years. Similarly, bulk of the coking coal that Indian industry uses to manufacture steel. India is the second largest steel producer in the world, next to China. But nearly 80% of the industrial coal or coking coal that is used for steel production in India is imported. Indonesia, Australia, and South Africa, and a few other sources. There's also some Russian coal and Russian oil and Russian gas that is coming into India. So this fossil supply in general, as well as the fossil fuel prices, are becoming increasingly risky and volatile, as we have seen in the last 2 to 3 years. And the third aspect about India's energy transition is clean energy is getting increasingly cheaper and ultra competitive with fossil sources. We've already seen with the drop in solar prices, with battery prices, and as a result with EV prices and so on and so forth. And again, we'll come to the detail in that. But the point is, this is the first time where the technical viability, economic feasibility, and environmental sustainability, the three most important dimensions of any energy transition. And last, the fourth dimension, which is becoming super important in the last few years, is energy security. So technical viability, economic feasibility, energy security, and environmental sustainability. All four dimensions of the energy transition are pointing in the same direction in India, and which is why energy transition in India is unique and needs to be seen quite differently from the conventional energy transition lens we use in the US or Europe or even in Japan. And what that means is the political economic alignment for energy transition is feasible. The entrenched interests in the fossil fuel sector are much smaller and manageable, and they can be replaced by new interests in the clean energy space as well. So what the charts on the top show is the levelized PPA prices, the power purchase agreement prices in dollars per megawatt hour in different countries for wind, chart on the left, and solar, chart on the right. The limited point of these two charts on the top are India has achieved some of the lowest solar or wind PPA prices or contract prices in the world. And this has happened not only because India has the best solar or wind resources. For solar, India definitely has some of the best solar resources in the world. But India has also done some pretty innovative policy making and pretty innovative regulatory framework that has helped them achieve such price reduction in wind and solar. And the chart at the bottom right shows the retail diesel price in India just in the last 20 years, starting 2002 to 2022. So the diesel price has risen by more than 5 to 6 times just in the last 20 years, which is a massive growth, which is, and this is also real price, okay? So this is a real price increase of approximately 8 to 9% per year over 20 years. So that's what I mean is the fossil energy supply is getting increasingly risky, volatile, and expensive. Now, what's happening globally in the clean energy space is, as I mentioned, the cost of clean energy has declined dramatically just in the last 8 to 10 years. But let's analyze what has happened and why it has happened, right? The chart on the left shows the solar PV module price in dollars per watt in the last 12 to 13 years. So starting 2011 through 2024. So the solar module prices, which is the building block of any solar panel, and that's why any solar energy-based power plant. So solar module prices have dropped by nearly 80 to 90% just in the last 10 to 12 years. And currently the module prices have fallen under $100 per kilowatt or $0.1 per watt, which is a dramatic reduction in the module prices, which used to be nearly $1,500 per kilowatt or $1.5 a watt just about a decade ago. But at the same time, the manufacturing capacity of the solar panels, which is shown on the chart on the right, has also increased dramatically. So the chart shows the total solar PV production or total solar PV demand in the world, which is shown by the blue line. I don't know if you can see my marker.
Yes, we can see it.
Okay, perfect. So this blue line shows the total solar PV demand in the world, which is today is approximately 500 gigawatts per year. So the world today installs approximately 500 gigawatts of solar PVs each year. Nearly 250 to 300 of them are installed in China alone. Nearly 20 to 30 gigawatts in the US, same number, 20, 30 gigawatts in India, and all other countries combined is another 100, 150 gigawatts, give or take. But anyway, the point is the total solar PV demand is 500 gigawatts, but the total solar PV production capacity is more than 1 terawatt or 1,000 gigawatts. So the manufacturing capacity of solar PVs is nearly double that of demand. Now, this has two implications. Implication number one is this overcapacity in solar PV production is here to stay, which means that the solar PV panel prices will continue to be lower and continue to fall over the next decade or so. And second is that also erodes manufacturer margins pretty significantly, because once you have overcapacity, you have to kind of short sell your PV prices. That reduces the manufacturer's margin. But at the same time, the solar PV supply chain is also diversifying. For example, this light blue color on these bars shows the manufacturing capacity is China. And then there are other countries such as India, US, Vietnam, and other European countries. They've also kind of accelerating their efforts to manufacture solar PV panels. So as a result, it is extremely likely that we will continue seeing the continued decline, not at the same rate though, but a continued decline of solar PV prices in the world over the next 5 to 10 years. Now, this story is not only limited to solar PVs, okay? Batteries, you see a very similar story. The manufacturing capacity of batteries, in fact, is nearly 4 to 5 times higher than the global batteries demand today, which implies that over the next 10 to 15 years, even if there are no new investments made in battery manufacturing capacity, you would still see a sustained battery cost declines, given how much battery capacity that we've already built or have started to build. So this is what I was talking about in terms of batteries. I mean, we already know. So just focus on the chart on the left. Okay, I think all of us already know how dramatically battery prices have dropped. So this chart on the left shows the battery pack price, the lithium-ion battery pack price uh, for the last 10, 15 years, starting 2010 all the way through 2024, which is actuals, and 2025 onward, it is a projection. Actually, I'm sorry. This number is 2023 number. This is the actuals are until 2023, and then a projection going forward from 2024 onward. So there are two interesting observations, right? Observation number one is just in the last 10, 15 years, the battery pack prices have fallen by 90%, from nearly $1,400 in 2010 to under $140 by 2023. That's a 90% reduction. And it is expected that the battery pack prices will continue to fall over the next 10 to 15 years. But what is interesting is this is what all of us experts, the BNEF analysts, all researchers in the world thought battery prices would fall in 2023. But industry has beaten all those forecasts. And this is what has already happened to battery prices just in the last 2 years. Focus the dates. May 2022 until April 2024. So what we thought the battery prices in 2022, 2023 were $140 per kilowatt hour, give or take. And look at this LFP, the lithium ferrous phosphate, or this is the most popular, most commonly used battery technology today is the lithium iron phosphate. So approximately $140 per kilowatt hour, $150 per kilowatt hour, that has already dropped to nearly $75 per kilowatt hour just in a span of 2 years, the last 2 years. And if you just go back to our expert projections, that includes myself and experts such as myself, we thought battery prices would be $80 per kilowatt hour by 2030. Well, industry said, sorry, we are going to beat those forecasts and $75 by 2024. It has beaten all the forecasts and taken everybody by surprise. And it is expected that in the next few years, the battery prices continue to fall at the same rate that we have seen so far. And why is that happening is what I was talking about. I briefly touched upon it, is the battery production overcapacity. So what this chart shows, the y-axis is the lithium-ion battery cell manufacturing overcapacity. Is the ratio of production capacity to annual demand. And if you look at 2024, the global production capacity, which is the black dotted line, is approximately 4 times higher than the current battery demand in the world. And if you only look at China, then because China also exports a lot of batteries, that number seems a little skewed, like 6 to 7 times higher, but 6 to 7 times higher than Chinese battery demand. But China also exports a lot of batteries. So we should really look at the global battery production capacity. So which implies that even if the global battery consumption increases by 4 times, we still have enough production capacity to meet that demand. And this is only existing production capacity. There are also massive new investments that have already been planned where the steel is in the ground for installing those new battery production capacities. So we will most likely see a sustained reduction in the battery prices even going in the future. And this is exactly what I was talking about, is the actual lithium-ion battery manufacturing capacity in the world. This is actual until 2024, so approximately 5,400 gigawatt hours per year of battery cell manufacturing capacity that we have today, which is expected to nearly double just in the next 2 years. So you can very well see what's happening to battery prices. So now coming back to what does this mean for some of these strategically important sectors for India? This drop in battery prices, drop in solar prices, and so on. So let's start with battery prices, okay? So one thing I did not really mention is This is again, the battery production capacity chart that we saw a few minutes ago. Just focus on this red part on the column, okay? Red is China. So currently in 2024, more than 80% of the global battery production capacity is located just in China. And that is largely going to continue, even though US and Europe, as well as India, other countries will ramp up their battery production efforts. China will still dominate the battery supply chain and battery production. And that is also being reflected in some of the strategically important sectors. So this chart is a little busy. Just follow my pointer, okay? So this chart shows are the actual number of passenger car exports by some of the key countries in the world. There's Japan, Germany, US, China, India. South Korea is not on this chart, but South Korea is very comparable to Japan and Germany. So the point is, these are some of the largest car exporters in the world. And Japan and Germany used to be nearly 5 to 6 times that of India pre-pandemic. India is this gray line, and they used to be nearly 2.5 to 3 times that of the US in pre-pandemic. This is the COVID-19 pandemic begins, 2019, 2020 or so. And look at China. So India used to export significantly higher number of cars than China until the pandemic. And of course, Japan, Germany were the leaders. Just see what happened after 2019 and 2020. China's car exports started to skyrocket. And this is a slightly older chart. This is only until 2023. We haven't included 2024 numbers. But if you look at 2024 numbers, Chinese car exports have already overtaken the Japanese or South Korean or German car exports, the leaders in the world. And this is mainly thanks to the EV revolution that has happened in China. 50% of cars that are produced and sold in China are already EVs. 50%. So that market has already transformed. It is the second largest car market in the world, but soon it will be the largest car market in the world. So other countries, particularly countries like India, really need to catch up, because now let's look at what's happening in India. Indian car exports have just been flat through pre-pandemic, no growth, despite the domestic auto sector really booming because of the rising urbanization and incomes, but they couldn't really increase their exports, and they stayed flat, and in fact dropped a little after the pandemic. And there is no growth in sight because India hasn't really caught on to that EV technology adoption like China or other countries have. Now, this has important implications. So auto sector in India is one of the largest employers of manufacturing jobs, largest creators of manufacturing jobs in the country. So falling or a failing auto sector also implies massive impact on manufacturing, well-paying unionized jobs. And that has significant political economic implications as well. So just in their own interest, India, and purely focusing on the jobs and manufacturing economy, it's imperative that India catches on to EV production and so on. I just wanted to take a pause here and see if there are any questions. Otherwise, we'll continue. All right. Well, I'm not actively monitoring the chat, so if somebody has put a question in the chat, I won't be able to see that right now.
Yeah, here's a question from Frank. Where are the Chinese car exports going?
Great question. So some of them are actually coming to India. Many of them are going to Europe. Many are going to other Southeast Asian countries, including Indonesia, some to Vietnam, because Vietnam also has their own auto industry, some in Malaysia, and so on. But many exports to Europe as well. All right. So with this context, uh, what we started thinking is, how should you think about India's energy transition? And what we decided on, let's look at three pillars of energy transition, especially for a country like India, which is not fully industrialized and really needs to grow its economy. So number one is, any energy transition should create large domestic dividends, meaning that it really needs to result in reduced energy costs, reduce energy expenditure, more efficient use of the energy, and so on. It should actually have quantifiable monetary domestic dividends. Then the second important aspect of energy transition is, again, especially for a country like India, it should think of opportunities that have a high export value potential, such as EVs, for example. So EV market, especially globally, has been largely captured by the Chinese EV manufacturers, because they've also started on that journey, pun intended, much earlier, at least 10 years ago, and so on. But there are several other opportunities where India can still capture significant export potential. One such example is solar PV, or solar panels. So India still currently exports nearly 30 to 40 gigawatts worth of solar panels to the US, which leads to my third point, is India should also think of opportunities that give India comparative advantage over other countries. For example, uh, many European countries, and definitely the US, would rather prefer a trade with India than China when the costs are generally equal. And of course, India cannot produce or cannot manufacture some of the goods as efficiently and at low of a cost as that in China. But sheerly because of the geopolitical alignment, India can still capture some of that export potential because it has a comparative advantage. And I'll give you an example. Electrical grid infrastructure, like transformers, transmission cables, and so on. It is typically, suppliers are unwilling to procure their equipment from China because it's a sensitive infrastructure and so on. India, on the other hand, has a huge electrical equipment manufacturing industry, and they do export it to many global South countries, many countries in Africa, many countries in Asia, Latin America, and so on. But India still has not been able to crack open the high value European or the US market. So this potentially is one opportunity where India can crack that export market, and so on and so forth. I mean, one can always start exploring many such opportunities, but the key point of this slide is we should really think of energy transition along these three pillars: is domestic dividend, comparative advantage, and high value export potential. And with these three pillars in mind, and given where technology is headed, where India has already started making some efforts in that transition, where the costs are, and so on and so forth, we identified what could be the top 10 clean energy strategies for India over the next 25 to 30 years. And what is interesting is India also has this aspirational goal of becoming an industrialized or becoming a developed country by 2047. So why 2047? Because 2047 also commemorates 100 years of Indian independence. India got its independence from Britain in 1947. And that's the aspirational and the political goal that the current administration has had set in India. So what we are essentially, whenever we talk with the Indian policymakers, this is definitely uh, uh, a clean energy strategies for making India a developed country by 2047. I'm not going to go into the details of each of those. We're only going to talk about three or four most important ones. First is the deployment of renewables and storage. And that is true globally, not just in India, but also in the US. Then we are also going to talk about green hydrogen, what should India be doing for industrial transition in general? What's the role of green hydrogen, green steel, green fertilizer, and so on and so forth. And we are also going to talk about electric vehicles and how the transition to electric vehicles in India is quite different from what we generally think in the US. Okay, we're going to focus on just these three: renewables plus storage, electric vehicles, and green hydrogen in industry. Okay. All right. So what this chart shows, if India adopts all those top clean energy transition opportunities that we have outlined, it mostly shifts to electric vehicles. It only builds renewables plus storage going forward and cleans up the grid by 90 to 95% over the next 20-25 years. And it shifts most of its industry either to electricity or steel production, fertilizer production shifts to green hydrogen. So decarbonized transport, decarbonized industry, decarbonized power can result in massive emissions, local environmental, and energy security benefits in India. Not all of these are shown on this chart. What this chart shows is just the energy-related CO2 emissions in the country over the next 20-25 years. If India does nothing, just does whatever they have announced so far, and no new policies are implemented beyond what they already have, what we expect is India's emissions would increase from nearly 2 gigatons today, 2.5 gigatons today, to approximately 4.5 gigatons by mid 2040s. And just for comparison, in the US, total greenhouse gas emissions are approximately 6.5 gigatons. Okay, so India is nearly third, a little over third of the US CO2 emissions today, and they will still be lower than the US CO2 emissions even if they did nothing until 2045. But what we are arguing is if India adopts this clean energy pathway, which will not only save their energy costs, but also create significant local environmental benefits and will nearly eliminate all fossil fuel imports in the country. And they can also reduce their CO2 emissions dramatically by nearly 95% by 2047 and 2050, in addition to avoiding over 4 million premature deaths due to local air pollution by 2050. So this is the big picture on on energy transition. What could be possible? Which are the key sectors they should focus on, and what would be the big picture impact? Now let's drill down on those three opportunities that I specifically talked about: is RE plus storage, EVs, and green industries. So let's talk about RE plus storage. So as India moves from IC engine vehicles to electric vehicles, as Indian industry moves from fossil fuel powered processes to more electrified and green hydrogen based processes, India's electricity demand is also going to increase pretty rapidly. And electricity demand is going to increase because of three factors. Number one, as I mentioned earlier, just the inherent growth in India due to rising incomes, industrialization, urbanization, and so on, which is captured by this black line. So the black line shows the inherent load growth in the country, which was approximately 1,500 terawatt hours in 2022-2023, which will more than double or triple over the next 20 to 25 years. That's a growth of around 5 to 6% each year. So India's electricity demand is doubling, almost doubling every decade or so historically, and it will continue to do so in the future. And as I mentioned, the additional causes of electricity demand is the transport electrification as well as industrial electrification and decarbonization through green hydrogen. So those two components would increase electricity demand in India to close to 7,000 terawatt hours by 2050, which is a growth of nearly 5 times just in a span of 25 years. This is a massive electricity demand growth we're talking about. And just for comparison, right, the US's current electricity demand is approximately 4,000 terawatt hours, give or take some. And depending on which projection you follow for the future, it is expected that the US electricity demand will increase to will nearly double or even triple by 2050, depending on how fast of an energy transition that we take. It could be as high as 8,000 terawatt hours to 12,000 terawatt hours by 2050. I am most, I would bet my money on that 8,000 9,000 terawatt hours number by 2050 in the US, but that is still a huge load growth in the US, especially relative to what we have seen in the last 25, 30 years in the US. In India, on the other hand, it will grow fivefold over the next over the next 3 to 4 decades by 2050 or so. That is equivalent to almost 7 to 8% per year of electricity demand growth, which is something that they've already met in the past. Again, I'm not suggesting that going from 1,000 terawatt hours to 1,500 terawatt hours is same as going from 1,500 terawatt hours to 5,000 terawatt hours. It's an order of magnitude difference. But still, the point is, India is also one of the few countries in the world, just like China, that can build infrastructure relatively faster compared to, say, for example, the US or even Europe. So what does this load growth really mean for renewables capacity? What this chart shows is how much renewable capacity would India need, or how much power generation capacity would India need by 2050 if it adopts a clean pathway and if electricity demand in India increases by nearly 5 times. Again, don't focus on the specifics of the numbers because they may not mean much. But the point is just focus on the total size of these bar charts. In 2020, the total electricity generation capacity in India was approximately 400 gigawatts, 250 gigawatts from fossil and nearly 150 gigawatts from non-fossil, which by 2050 will have to increase to nearly 3,500 odd gigawatts. So just the renewable capacity need to increase to 2,500 gigawatts, a massive growth. And that implies a new investment in clean energy assets of more than $300 billion by 2030 and up to $1.5 trillion by 2050, a massive, massive scale. And just for comparison, the total renewable energy capacity for a cleaner energy economy in the US we're talking about is approximately of the ballpark of 3,000 to 3,500 gigawatts of renewable capacity by 2050 if US needs to achieve net zero emissions by 2050. So this is in the same ballpark. And before we talk about the other sectors in India, I'm just want to give you some flavor of this rapidly falling battery and solar prices, what they're doing in the US as well, right? So chart on the left shows the existing battery installations in the US, which are approximately, this is a slightly older number. So the current battery installations in the US are approximately 25 gigawatts. Out of those 25 gigawatts, nearly 10 gigawatts of batteries are installed just in California. And 50% of the batteries that we see in the US are co-located with solar. But what is interesting is if you look at the chart on the right, that shows the US interconnection queue. Interconnection queue meaning that essentially developers have shown interest in installing some renewable energy capacity at 100, 200, 500, as the case may be. And they have made an interconnection application to the transmission utility for them to connect the renewable project to the transmission system, which means this is not just some random announcements on paper, but these are some serious announcements. So nearly 1,500 gigawatts of renewable capacity is in the US interconnection queue. 1,100 gigawatts solar, 350 gigawatts of wind, including some offshore wind. In addition, 500 gigawatts of standalone batteries are in the interconnection queue. And 95% of the solar capacity that is proposed in the Western United States comes with an addition of some level of energy storage, particularly batteries. So even in the US, a massive transformation is just about to happen. And there are many reasons. I wouldn't go into the details of why we see this rapid transformation even in the US, but it is happening and it is very real. And as I mentioned, this 1,600 gigawatts of solar plus wind capacity that is in the interconnection queue, not all of that is actually going to materialize. Only a fraction will actually materialize. But nonetheless, this is a huge jump from where we are in the US. And that is also being reflected all over the world. All right. So moving on. Let's talk about electric vehicles in India. Okay. So typically, when we talk about electric vehicles, the conventional wisdom says we should just talk about electric cars, and that's what we usually visualize in our minds whenever we talk about EVs and electric vehicles, either Teslas or other swanky electric cars. But India is slightly different. Let's focus on the chart on the left that shows the oil consumption in India by different categories of vehicles. And oil consumption in, well, not just India, but also in multiple countries. It's US and EU and so on and so forth. So trucks and buses, just focus on trucks and buses. Trucks and buses are this blue and this brown area in these columns. And cars, passenger cars, is this red area in the column. So if you look at the US, 70% of our oil consumption, nearly 70% of the oil consumption happens in passenger cars, and only about 30% of the oil consumption happens in trucks and buses. Whereas in India, this proportion is exactly opposite, meaning that 70% of the oil consumption in the transport sector happens in trucks and buses, freight movement and bus heavy passenger movement. And only about 30% of the oil consumption happens with the smaller passenger vehicles, and that includes two-wheelers and three-wheelers, so small mopeds and tuk-tuks and so on. So the cars account only for about 15 to 20% of the total oil consumption in the country. And about 15 to 20, about 15% or more in the two-wheelers and three-wheelers segment. And so that's why this EV transition in India also needs to be looked at quite differently. Not only passenger car or car focused, but more of a truck and heavy-duty vehicle focused transition to electric vehicles. So now let's look at the chart in the middle. Right? Chart in the middle shows the crude oil production and imports in India, or the crude oil consumption split into imports and production in India. So of the total crude oil consumption, nearly 90% of India's crude oil is imported, which is equivalent to $150 billion per year. This was 2022, before the crazy oil price spike really hit the country. But around 2023 onwards, we're talking about an import bill of $200 to $250 billion each year, which is close to 7 to 8% of India's GDP just going on importing oil. And this is a huge concern, not just from a trade balance perspective, but also from an energy security perspective. So as I mentioned, the EV transition in India really needs to focus on trucks. And of course, that doesn't mean that the cars and two-wheelers and smaller vehicles are not important, but trucks should be the front and center of India's transition story. Now, the conventional wisdom, or not just conventional per se, but even if you talk with many researchers, what they would say, well, the trucks are very heavy, the truck batteries are super heavy, cars are okay, car batteries are much lighter, but trucks are different. They have to drive for long range, 300 miles, 400 miles, even 500 miles. And at that distance, the batteries just don't make it. And that's why we need to use hydrogen for trucks. You might have heard this discussion either in different forums, or you might have also read papers about it. But just purely based on an energy efficiency perspective, that logic just does not make any sense. So what this chart shows is the total energy input that will be needed to drive a 500-mile truck, a 40-ton, a typical Class 8 truck for 500 miles. So if you just use an electric truck, you generate electricity, you store that electricity in the batteries at an efficiency of 90%, then you draw that electricity onto your truck, which is again at an efficiency of approximately 90%, and then you store that electricity in the batteries of your truck, which again at an efficiency of approximately 90% or so, give or take, you are talking about an overall system efficiency of approximately 75 to 80%, give or take. Now, if you look at hydrogen, there are so many inefficient steps involved in between for driving a hydrogen truck. You generate electricity. You convert that electricity through electrolyzer to hydrogen. Electrolyzers operate, best case efficiency is 70%. It's actually lower than that, but best case is 70%. Then you compress the hydrogen, put it through hydrogen pipelines. Again, that compression and pipeline efficiency is approximately 90%. Then you store the hydrogen and then you pump it into your truck. Again, approximate efficiency of 75 to 80%. And then you use your fuel cell, or in some cases, hydrogen engine in your truck at an efficiency again of 50 to 60% or so. Best case 60%, 65% efficiency within the truck. So the overall system efficiency is easily less than 50%, 45 to 50% efficiency. And as a result, you need to generate 5,000 kilowatt hours of electricity to drive 800 kilometers of a hydrogen truck, compared to just 1,000 kilowatt hours of electricity drive 800 kilometers for an electric truck. So hydrogen trucks just do not make any sense purely from an energy efficiency perspective. So this is a slightly controversial view because there is so much work done on hydrogen trucks. So I would love to just pause here and see if there are any questions on this topic.
Yes, Nikit, there is a question from Carlos Romero. This comparison for electric versus H2 trucks is based on the current state of affairs. Does it
Yes.
include future progress in electrolyzers?
No, this does not include future progress in electrolyzer. This is based on the current state of affairs. But this also assumes a generous efficiency of 70% for electrolyzers, which usually you would only get about 60 to 65%. Even if you change that electrolyzer efficiency to, say, 80%, 85%, that still doesn't change the equation in a substantive way.
Yeah. So I guess I'm trying to put Carlos's question with what you've talked about. You've pointed out that India needs to concentrate on electrifying or decarbonizing the truck fleet rather than the car fleet as the Western countries are looking at. So if you were to consider hydrogen for doing the decarbonization, that's an inefficient process. Is that correct?
That is exactly right. So hydrogen doesn't make any sense because this doesn't even include the cost of building the entire hydrogen infrastructure, hydrogen pipelines, the pumping station, the compression stations, the storage, and so on and so forth.
Okay. So it is because of the context in which decarbonization is taking place. You know, the focus is on heavy duty vehicles in India. And I suppose this is probably true for other Southeast Asian countries. I'm not sure. But if hydrogen is not a good candidate, let me put it that way.
That's right. That's exactly
Okay.
right. Hydrogen is not a good candidate. I think one of the, again, we can discuss more a bit later, but I think one of the reasons why countries are also looking at hydrogen is because how concentrated the battery supply chain is with China, right? So, so then one of the common criticisms is, well, yeah, that's okay. We are not importing oil, and we have heard this from India is yeah, we are not importing oil, but we are essentially importing batteries. So what's the difference? So what's the energy security there? I think there are multiple responses to that. I think one of the critical differences between oil and battery is that battery is necessarily a capital asset and oil is a consumptive asset. So once you consume the oil, you need more oil like tomorrow once the consumption is done. But once you have those batteries, you have those batteries until they die, which is around 10, 12 years or so. That's number one.
Okay.
And number two is you can also set up your own battery supply chain, which India has already started doing, but not at the same scale or pace at China. But they have the opportunity and the chance to do it like we are doing it in the US. It won't be as cheap as as China could do it, but it won't be too expensive.
Okay. We have another question in the chat. Let me see if I can bring it up. From Libin, what aspects are used for this comparison? How about comparison in terms of refueling speed and driving range?
Sorry, can you
Yeah.
state the question again?
What aspects are used for this comparison? I suppose comparison between electricity, decarbonization of the truck fleet with hydrogen versus electricity. What
I think
aspects
this.
are you? Go ahead.
No, refueling speed, et cetera, is not considered here, and that is
Okay.
definitely one aspect that needs to be considered. But I would argue, I mean, this comparison is purely based on energy efficiency. This doesn't even include any costs, right? And in fact, if you look at costs, electric trucks would beat hydrogen like even more, even more dramatically than just energy efficiency. This is purely energy efficiency. Refueling speed needs to be considered, but that is not that big of a concern for trucks because they usually have very long drive cycles. They drive for 8, 9, 10 hours in a day. So that's why they have significant opportunity to schedule their charging, to schedule refueling, and 30 to 45 minutes to 1 hour refueling or recharging could be scheduled when they have their mandatory rest stops anyway.
Okay, no more
All right.
questions so far. Go ahead.
Okay, so let's moving on. So what is interesting is, again, I'm not going to go into the details. This is a pretty busy slide, and I'll be happy to share our research paper based on this research. But what we are finding is across all vehicle segments, which is two-wheelers, which is the small scooters and the motorcycles, the passenger cars, as well as heavy-duty trucks, electric vehicles on a total cost of ownership, dollars per kilometer or dollars per mile basis, electric vehicles are already cheaper than IC engine vehicles across all vehicle categories. But this is, again, the key caveat is this is on a dollars per mile basis, a dollars per kilometer basis, even in India. So it's really just the question of addressing the first cost barrier of electric vehicles, addressing the charging infrastructure barrier for electric vehicles. That is really critical to make sure India embarks on this EV pathway. And the charging infrastructure discussion in India is quite different than it is in the US, right? In the US, most houses have access to garages, to driveway, to dedicated private chargers for their cars. But that's not the case in India. Most houses are multi unit apartment complexes, say all of them may not have a dedicated parking spot. Even if they do, they may not have access to an electrical charging system there. So public charging infrastructure and fast charging becomes even more critical for EV transition in India than in the US. And there is significant activity in that space by the government, but not as much or not as fast as they should have. For example, they are currently electrifying or building charging infrastructure along all major freight corridors and highways in India. But that should be done faster for truck owners to actually adopt these electric trucks. All right. So I'm just going to skip this in the interest of time. So one of the common questions that we always get asked is, well, what about lithium? If India really goes along this led EV-led growth, and if India really builds a lot of batteries even for the grid, what about the battery supply chains? What about lithium? Wouldn't India just be importing lithium? Then the answer is pretty exciting and also surprising. The exciting part is India has already found significant amount of lithium reserves, and compared with how much lithium India would need, which is shown on the chart on the left, is the cumulative lithium demand in India if India embarks on this clean energy pathway, would still be much smaller than the lithium reserves that they have already found. Just this was 2023, and they have found more reserves just in the last year or so. So that essentially implies that in terms of lithium supply, India may not necessarily have to depend on imports. But of course, this is easier said than done. These reserves have just been found. For those reserves to actually turn into resources and turn into actual production of that lithium, there is still a long gestation time that one needs to account for. But this is where the advantage that India has, because India's vehicle market is not as matured as the US vehicle market. India still has time to build those supply chains and still not lose a lot of steam on this electric transition. And then the other interesting opportunity for using lithium is also recycling lithium. As you would already know, nearly 95% of the battery materials in spent batteries are fully recoverable and fully recyclable. Even in case of lithium, for example, that lithium is still fully reusable after if it could be extracted or if it could be recycled from the spent batteries and could be reused in new batteries. Of course, that supply chain is not fully existent even in the US, much less in India, is almost non-existent. But again, the point is that is also this recycling lithium and other battery material from spent batteries is a huge opportunity that India should focus on, especially for managing lithium imports as well as other battery supply chain issues. Now let's move on to industries and green hydrogen. And I'm just going to spend no more than 5 minutes on this, okay? So hydrogen, so has been a lot of talk about green hydrogen that you would have heard. And hydrogen is of course the most abundant chemical element in the universe. But the key is that doesn't matter. On Earth, we have to obtain it from the energy sources that we have available on Earth. And you might have already heard there's several different distinctions of hydrogen. There is gray hydrogen, which is produced mostly from natural gas, and obviously has a very high carbon footprint. Then there is blue hydrogen, which is still produced from natural gas, but sequestered carbon dioxide emissions. Then there is purple hydrogen, which is produced from nuclear energy. And then there is green hydrogen, which is essentially produced using clean electricity obtained from solar and wind or other renewable sources. You put that electricity through an electrolyzer that splits the water atom, the H2O water atom, into hydrogen and oxygen, and then that's how you get hydrogen. But the key challenge with this green hydrogen is it is still pretty expensive. It is significantly more expensive than just the gray hydrogen, which is produced purely from natural gas, and definitely significantly expensive still, even if you want just a flat block of green hydrogen, meaning that you want green hydrogen supply 24/7 at flat block. That is still far more expensive. And what we are projecting is even in the future, 2030, 2040, 2045, the green hydrogen cost would still be more expensive than gray hydrogen. We just have to accept that as a fact. And that's why we need some massive improvements in electrolyzer technology. And that too, no rocket science improvements in electrolyzer technology, just using simple low-cost electrolyzer technologies can essentially go a long way. Second is we need some innovations in hydrogen storage. Again, I wouldn't talk a lot about hydrogen storage. I'll be happy to take questions later. And third is we also need some innovation on how that hydrogen is used. For example, instead of storing hydrogen, can we use hydrogen whenever it is produced by changing our industrial processes to a certain extent? With these three factors, electrolyzer innovation, hydrogen storage innovation, and industrial process innovation, there is actually a very clear pathway for this green hydrogen price to be comparable to gray hydrogen price. Now, having said that, it is still a long way. It is not happening in the next 3, 4, 5 years. It is still 10 to 15 years away. So just to set the expectations right. So even in the industrial space, right? And this is more of a global schematic for what are the good and excellent uses of hydrogen, and what are some of the poor or terrible uses of hydrogen. These also apply for India as well as United States. So what are some of the excellent uses of hydrogen? Is using green hydrogen in refining, using green hydrogen to make ammonia-based fertilizers or urea, for example. Using green hydrogen for producing green steel, aviation fuel, other petrochemicals, etc. These are some of the good and excellent uses of hydrogen. What are the terrible uses of hydrogen is using hydrogen to generate electricity, using hydrogen in our vehicles, using hydrogen for buildings, for heating and cooking, etc., etc. These are absolutely terrible uses of hydrogen and need to be avoided. So with this in context, so we started looking at India's steel industry. So that's one of the good uses of green hydrogen. And how can green hydrogen help decarbonize India's steel industry? So just to explain the process, this is a slightly complicated chart, but what essentially happens is green hydrogen is essentially used in the direct reduction iron furnace, the DRI furnace. That essentially gives us the iron. That iron is put into electric arc furnace, and that electric arc furnace essentially gives us the green steel that we want. So renewable energy produces through electrolysis, produces hydrogen, which is put into DRI furnace, and the hydrogen essentially here acts as the reductant, right? So iron ore, which is ferrous oxide, Fe2O3, reacts with hydrogen, and that produces Fe, which is iron, plus H2O, steam and water, which iron then put through electric arc furnace, and we get the green steel. But the interesting point is, I think, as I mentioned earlier, India currently is the second largest producer of steel in the world. The first largest is China. China produces nearly 1 billion tons of steel every year. India produces close to 120, 130 million tons of steel every year. So there's a massive growth in the steel production in India that could be driven purely based on domestic demand from India in terms of the roads they're building, the buildings they're building, flyovers, and other infrastructure. So India's steel production is expected to nearly quadruple over the next 20 to 30 years, from nearly 130 million tons in 2023 to close to 400 to 500 million tons by 2050. And this is again goes back to my point of leapfrogging. So 75 to 80% of India's steel production capacity that will exist in 2050 is yet to be built. And that's why there's this huge leapfrogging opportunity to green steel that India can capture. Of course, green steel is going to be more expensive than the conventional steel. And the key is getting cheap green hydrogen. That is the only way to get green steel, because this is not really a technology play. We generally know the technology for green steel production because there is already a lot of steel production that happens using natural gas. And natural gas also produces a green steel, not green steel, I'm sorry. Natural gas furnaces also produce steel in a very similar industrial process. So hydrogen-based green steel production is not necessarily more of a technology play than more of an economics play. So bringing the cost of green hydrogen to under $2 per kg in India is absolutely critical for green steel to be more cost effective and comparable to the conventional coal-based steel. There are multiple ways in which one can reduce the cost of green hydrogen. I think the most critical, as I already mentioned, is bringing the cost of electrolyzers. Electrolyzers today cost anywhere between $1,200 to $1,500 per kilowatt, which needs to be brought down to under $300 per kilowatt or so. There is a pathway that can happen. For example, in the US, they usually use an electrolyzer called PEM electrolyzer. Chinese usually use an alkaline electrolyzer, which is performance-wise a little inferior, but cost-wise 80% cheaper. So there is some innovation that definitely can happen in using alkaline electrolyzer for green hydrogen production and so on and so forth. Again, I'm not going to go into the details, but the point is bringing green hydrogen cost under $2 per kg is absolutely critical. And this is obviously critical for India, but this is not just India. This is also true globally. So I think let me stop here and see if there are questions. I'm happy to elaborate on any other topics that you would like.
So Nikit, let me just take the question that has been in the chat box. Let me make sure I get the right person. Frank Richards, why no major focus on nuclear generation in India?
Sheerly because of cost and how long it takes to build a nuclear power plant. So India has been wanting to build nuclear. I mean, India has a lot of thorium reserves. They want to build nuclear power based on using thorium technology, but they have not been able to do it. And the costs have been very high.
Okay, this is the formal Q&A session. I normally give preference to students to ask the questions first. So now I'm asking the students in the audience, please unmute yourself and introduce yourself and ask the question from Dr. Abhyankar. Students? Yes, Sajjad? Go ahead.
Hi, my name is Sajjad Al-Shammari. I'm a student in ESE. Thanks for your presentation. It is good and nice. I have a question. If they are increase the car for electric car and everything become electric, the price for kilowatt will be increased or decrease? Thank you.
I think the price will actually decrease. And the reason is, well, it depends how you use it, but uh, uh, the prices for renewable sources are essentially dropping. So going forward, the electricity price is likely to decrease in general. And what is interesting is if you use electric cars or particularly electric trucks, they also offer some flexibility on when they can charge. And as a result, you can charge them when electricity prices are the cheapest or when the market doesn't need a lot of electricity. So say right in the afternoon when you have a lot of solar. And so as a result, I do believe the electricity prices would actually reduce.
Okay, thank you, Sajjad. Thank you. Any questions, any more questions from students? Please unmute yourself. Introduce yourself. All right. Questions from the general audience? While we're waiting, Nikit, oh, sorry, Hamza. Go ahead, Hamza.
Hi, very nice to meet you, Dr. Abhyankar. My name is Hamza. I'm a student here at the university, at Lehigh University in Energy Systems Engineering. I have a question for you. It's a non-technical question, but I just wanted to know your opinions on how does the political and the social background of India affect the development of clean energy sources and the transition into clean energy resources. Basically, to simplify my question, what I mean is there's a lot of development in technologies and the transition into clean energy. Despite that, there's still a lot of poverty. A lot of the common folks are not even aware about the transition. They don't care about it. There's no active participation by majority of the population. Why do you think that is? What do you think can happen? What do you think the government can do? And what do you think the future looks like?
Great questions. Great questions. Well, I mean, so nearly 75 to 80% of India is really lower income or even lower, right? So obviously they're not thinking about transition in the sense that we are thinking. But there are some impacts that they face on a day-to-day basis. For example, local air pollution, local environmental impacts. The lower income communities, the frontline communities, there have been documented studies that show that low income and frontline communities face the largest brunt of any local environmental impacts. So they do care about those in terms of their health impacts, in terms of the water, and so on and so forth. So not from a climate or energy transition perspective, but purely from the local impacts perspective, they do care. Second is cost of energy becomes extremely crucial for them. And they do care about that. And this is where clean energy, if you had asked this question 5 years ago, the answer could have been quite different. The 5 years ago, the wisdom was there would be some additional costs because of clean energy transition. But today, that is not true anymore. The costs would actually be lower than most fossil alternatives for most end users. Be it from as simple as your electricity prices, or be it as simple as the bus or the truck operating costs that includes your freight transportation costs, your bus passenger tickets, and so on and so forth. And what is interesting is because these clean energy prices are also nominally flat for the next 25 years, they're not affected by inflation at all. So in real terms, those prices are actually dropping over years. So cost is the second factor that they are indirectly in general in favor of this or they would be in general in favor of the transition. I think where things would be quite interesting and might introduce some friction are jobs. For example, bulk of the coal in India is manufactured in the eastern part of the country. That is also some of the poorest regions. The classic resource curves is the poorest parts of the country. And as India moves away from coal, those jobs essentially will go away and will go away from the poorest regions of the country. But at the same time, this is where I think I mentioned, since India has that runway of 10 years or so to plan for that massive job transition, there are opportunities for creating retraining of the workforce and creating newer economic opportunities on those regions. But in general, political climate it's quite favorable for clean energy transition, and locally also as a whole, there is no major opposition to clean energy transition except for the jobs piece, and that is emerging to be a quite important one.
Got it. Thank you, Dr. Abhyankar. I appreciate you very much.
Okay, another question in the chat box. What is the market design structure in India?
I mean, I presume you're talking about electricity.
Probably,
market
yeah,
design structure.
yeah.
It's quite similar to the US, meaning that there are utilities, there are generation companies. They either have a long-term power purchase agreement, they have a long-term power arrangement, or utilities are also free to buy electricity from the wholesale electricity market, which works exactly the way it works here in the US, is on a day ahead basis, 24 hours ahead. And the generators essentially bid in the market. This is how much I'm willing to sell in the market, and this would be my cost. Utilities or load serving entities in general, or electricity buyers in general, also bid in the same market. I'm willing to buy 500 megawatts at this and this price. The supply curves and demand curves intersect, and that's where you discover the price in the market. So that's pretty much similar. There are two main differences compared to the US, though. In India, nearly 60% of all of electricity generation is still owned by some form of government. It's either the state government or the federal government. So the generators are not necessarily profit maximizing. So it is unlikely that you would actually see something like what happened in Texas in India, where the generators just literally made $9 to $10 billion in a matter of 1 week. It's unlikely that will happen in India. And the second big difference is most utilities, like 90%, 85 to 90% of electric utilities in India are also public. Public meaning owned by the state governments or the municipal governments. And they are also unwilling to pay extremely high prices in the market. They would actually shed load than buy electricity in the market. So for those two reasons, the market is not as vibrant as you would expect for a country like India. But nonetheless, nearly 15% of all of India's electricity is bought and sold and traded through electricity market. The same share in California is approximately 35%. 35 to 40% is through market, 60% is through long-term contracts. India is like 80-20.
Okay, questions for Dr. Abhyankar? Chat box or audio? Questions? Okay, so let me ask two questions, Nikit. This is somewhat quite different. One is, you talked about, in India today, renewables are truly very competitive. So when you think about a large amount of population has not reached the level of the quality of life or the income levels that the quote middle class in India has, are they better off if they were to be supplied by electricity with small microgrids? Does it make more sense? And not only more sense in the sense that they get energy more frequently, but the cost would be more bearable.
No, I think microgrids would be significantly more expensive than
Okay.
centralized conventional grids. And for main reason is that India has done a great job of expanding electricity grid
Okay.
to most places, and centralized system would always be cheaper than
Okay.
micro systems, sheerly because of the capacity factor and economies of scale.
Yeah. The other question is quite different. China, you showed, is it kind of dominates the renewable energy market in what they, how much they produce, how much they utilize. So, if electrification were the answer for most of our problems, are we still facing the fact that there's one supplier or one entity that could change the geopolitical situation at any time?
No, and that is a very, very important concern. And that's a very valid concern. And that's why all countries want to develop their own supply chains. And just to extend that argument further is currently we have 4 independent energy systems, right? Energy grids, so to speak. There is an electricity grid, of course. There is an oil energy system. There is natural gas energy system, and there is coal energy system. But so essentially, with electrification, we are combining all of them into just one single electricity grid. So on the supply chain side, you're absolutely right. All of our energy sources follow the same supply chain. So if there is any disruption in that one single supply chain, it spills over. And second, it's also a reliability question within the country. If there is one single point of failure at electricity grid, all your energy systems essentially fall apart. So those are very valid concerns, and I don't think there is an easy answer there, other than the countries need to have at least some of their own energy systems and supply chains set up.
Good. Well, thanks a lot, Dr. Abhyankar. This has been very, very informative. Would you be able to share your slides, or even if you would, with our students, because part of their assignment would be to write a paper on this, and we also produced a Zoomcast, almost like a pros and cons of what they heard, and we'll be glad to share that with you. So if you could, if we could get copies of your slides, that'd be really great.
Yeah, happy to share. No problem.
Perfect. All right. Thanks a lot, Nikit. And we go on a field trip. This class is going on a field trip to Con Ed next week. And 2 weeks from then, we'll have the 5th seminar. And it's going to be on energy storage by Eva Gardo, program manager at EPRI. But we'll continue this theme of energy transition in different locations. You heard today how a country like India has got so much white space, as it were, to look at different options, but they need to play some cards very carefully. We heard from Uruguay that they had no choice but to embrace green energy. Of course, it was a much smaller country compared to India, where the choices may be many, but the risks are equally high. And we'll hear from what the experience is in Australia 3 weeks from now. Well, thank you all. Thank you, Nikit. Nikit, if you can stick around for 4 or 5 minutes after everybody turns off. Thank you.